Welcome to Energy Talks, a regular podcast series with expert discussions on power system testing topics. My name is Scott Williams from the podcast team at Omicron, and I will be your host. Hello, everyone. In this episode, we will learn about the concept of the digital twin and its application in the electrical power industry. Basically, a digital twin is a virtual representation of an object or system that spans its life cycle. The digital twin is continuously updated with real-time data and uses modeling, simulation, and machine learning to help with decision-making and asset planning. With me to tell us more about how a digital twin is used as a tool for diagnosis and condition assessment in electrical equipment is Professor Michael Hartje from the Bremen University of Applied Science in Germany. He recently gave a presentation about this topic at the Omicron Diagnosis Week conference, which was held this year in March. I am pleased to have him here as a guest so that he can share his knowledge about digital twins with you. Professor Hartje tells us more about the connection between the digital twin and the monitoring, diagnosis, and control of electrical equipment. He also describes how the digital twin can be used as a single source of data about power equipment and how it supports decision-making for its continued operation. Specifically, Professor Hartje explains how digital twins are being used for the diagnosis and condition assessment of power transformers, which has been the focus of his work. Professor Hartje, welcome to Energy Talks.
Hello, Scott, and thank you for inviting me to this podcast.
You're very welcome. Professor Hartje, what is your area of specialty at the Bremen University of Applied Science?
At the university, I deal with high-voltage technology and, in particular, with digital measurement technology. At the same time, I also have a teaching position at the Graz Technical University for digital measurement and automation technology.
Professor Hartje, what is your background and focus in the diagnosis and condition assessment of electrical equipment and networks?
In the past, I have mainly dealt with partial discharge measurement technology, a particularly informative technique for evaluating insulation systems that are under voltage stress with regard to the expected remaining service life.
Getting to the heart of our discussion, could you please describe the concept of the digital twin? What is it and how does it work?
From my point of view, the concept of the digital twin represents a further development of the diagnostics of important parts of the electrical energy supply system and especially important equipment that have been in use for decades. I think we will get into the details in the course of the conversation.
Very good. What has been your work in this area, and why have you focused on power transformers? Can it also be applied to other types of electrical power equipment?
Thank you. Yeah, nice question. Power transformers in electrical energy networks are a central point of maintaining the electrical supply at all voltage levels. All of the energy flows through this equipment. So when you start dealing with the resilience of electrical networks, you will always look at the most important parts of such a network first. However, since I have continuously dealt with transformers and their service life over the past few decades, it seemed to me that this would also be a suitable object for this new question. In this respect, the concept of digital twins can also be transferred to other equipment and especially in the low voltage network, to the entire network.
Very good. So what impact or significance do digital twins have in the electrical power industry?
Thank you for this question. Yes, digital twins are a further development of conventional assessment methods for equipment. In this respect, they will concern both manufacturers and operators of electrical networks to a considerable extent in the future. It is likely that everyone involved will look into it and use it as a new tool for documenting and predicting the behavior of equipment and networks. Maybe we'll get to it later. The electrical power industry is moving into this topic in a similar way to other industries now.
Interesting. Okay. So what key areas does this concept of the digital twin support in the electrical power industry?
Thank you for this question. It gives me the opportunity to enable our listeners to transfer their questions. Employees of a company always have the same question when they look at keeping their jobs. This is exactly where the digital twin can provide support for the future. So, for example, when it comes to reducing costs, improving the efficiency of the transmission system, while facilitating on-site service through better preparation, while improving the operational reliability and service life, as well as the resilience of the transformer and the entire transmission system under consideration. It should and will thus relieve and support the asset manager in the decision-making process.
Interesting. So how is the concept of the digital twin a key component, for example, of Industry 4.0?
In my opinion, the digital twin of our technical objects is an important step in getting a better grip on the problems that can be observed in the day-to-day operations. Specifically, this includes the fact that technical information is not sufficiently openly transportable and efficiently available in an environment influenced by the Internet of Things, which is often known as IoT. Important information from the operating side, and by that I don't just mean those where errors occurred, are missing completely or slow down the further development of products and services on the manufacturer side, the operator side, and the service providers.
Interesting.
Finally, those involved in the service process and those responsible for the further development of products and services observe that a large part of the time is spent on too many routine activities. Concept of the digital twin are intended to reduce this.
Very good. So how does the concept of the digital twin optimize transformer operation?
Thank you for this question. It gives me the opportunity to once again go into the optimization of the operation of transformers. That applies to several areas of work. On the one hand, there is network operation and load management. We know that the utilization of the transformer and the associated heating reduces the service life of the insulation system of a transformer. When optimizing the utilization, we want to achieve a minimum lifetime consumption. Furthermore, asset management and maintenance, including the manufacturer, will have a great interest in determining the point in time at which operations are interrupted and carrying out as little maintenance as possible, thus making an optimal contribution to maintaining the service life.
So here we're really talking about condition-based maintenance. Is that correct?
Yeah. After all, It is about the diagnostic options. One of the essential principles is to carry out offline diagnostics before online diagnostics, both requiring planning, which the digital twin will offer support for. Finally, by linking several individual diagnostic results, it is also a question of improving the reliability of the diagnosis in a specific case.
Very good. So how does such optimization work? How is it performed in actual practice?
Yes, that's a great question that takes me back to the college. Mathematical-oriented engineers and, of course, artificial intelligence today proceed as follows. Try to define as many connections as possible in equations and mathematical expressions. All influencing factors should be taken into account. Then you get a large system of equations. By mathematically deriving, setting to zero, and solving the same system, and take the initially condition into account, it gives us a mathematical optimum. Finally, of course, one has to make sure that it is not a local but a global optimum. An alternative consists of carrying out various simulations on the system to be optimized and looking for the optimum therein. But also trained artificial intelligence systems and neural networks allow to somewhat more pragmatic approach. If you give some space to the question of how to set up models for mathematical optimization, the following procedure is generally used. All influencing variables and their weighting must be named. At the same time, a clarification of the language regulation is achieved for all parties involved. Sometimes, however, initial conditions and their dependencies have to be identified and described. Of course, this also includes the current state of the object as the initial state. A significant reduction in complexity can be achieved by identifying and deleting influencing factors that are linearly dependent on one another before the optimization starts.
Okay. Professor Hatya, could you please describe how an electrical asset, such as a power transformer, is connected to its digital twin? What is the interaction that takes place?
The digital twin attempts to depict the reality of the physical object. To do this, information must be exchanged alternately between the two. SCADA systems are now widespread in the upper voltage levels of energy systems. If we look again at the load management, they can provide the temperature that is necessary for further simulation or calculating of the operation behavior with changed parameters. The digital twin was then trigger the corresponding control.
Okay.
It could be generally known that machine learning requires a large amount of information from different operating cases to describe these relationships to create the greatest possible similarity between the twin and the physical object.
Very good. So how does the life cycle of the transformer correlate with the life cycle of its digital twin?
Well, the digital twin and the transformer have a very similar life cycle flow. physical design corresponds to the development of the digital model of the transformer. The production of the transformer corresponds to the instantiation of the digital model. With the commissioning of the transformer, the physical and digital object must, of course, also be connected to each other. Then it will be possible to provide database digital service in the digital twin.
Interesting.
At the end of transformer's life, the product status is determined and saved in the digital twin and archived, of course.
Very good. Professor Hartje, what are the differences between a digital model, digital shadow, and a digital twin?
Thank you for that question. It gives me the opportunity to point out that these terms are sometimes used interchangeably in today's professional communication. So let me try to explain the terms in more detail. The digital model can already exist without there being a matching real transformer. Therefore, it does not need any communication with a real transformer. Of course, which one? The digital shadow knows an automatic flow of information from the transformer to the virtual model. This is already common in many transformers today. Usually, there is then a manual flow of information back to the transformer. For example, performing a service activity. The digital twin, on the other hand, has both the digital model and a concrete transformer. The most important thing, in my opinion, the prerequisite for being able to call it a digital twin is the fact that there is a continuous two-way communication in real time, which feeds the digital model with appropriate updating of the information and thus makes it digital twin.
Okay.
The digital twin has methods and algorithms for integrating the information supplied into a simulation, and it is even able to independently carry out pre-calculations or simulations. This can happen in the background without someone explicitly formulating requests to the twin.
Okay. Professor Hartje, what are the different applications for a digital twin? Could you please describe them individually and which ones are related to equipment diagnosis?
Of course, there are also very different applications for the digital twin on the transformer. First of all, we differentiate more generally between a component twin and an asset twin. Which describes the entire equipment. A system twin, which also considers the environment, and a process twin, which can digitally map and simulate the entire process. The diagnosis of the transformer typically deals with the diagnosis of devices and components. So that the focus here is on the component twin and the asset twin.
Okay, so what are the components of a digital twin for a power transformer?
Well, to clarify, the digital twin of a transformer can include a 3D model of the transformer with the detailed geometry, information about the materials, and the manufacturing process of the transformer, calculations and simulations of the magnetic behavior under different load conditions, but also the current data from the environment and about the transformer. For example, load, temperature, the last surge loads, and no load currents, or just observations on the top changer. Furthermore, methods and algorithms for analyzing and predicting the future behavior of the transformer under different operation conditions are available in the digital twin.
Okay.
Possibly all algorithms for how the new observations from the operation data should be used, for example, to send warnings to those involved in the process.
Okay. Well, that brings up a point. What are the requirements then for a digital twin?
The digital twin is an extant concept of today's existing procedures. Of course, this means that some extensions are necessary compared to today's procedure. As a rule, this includes good real-time measurement technology and as many different sensors as possible, which also record different physical variables. There must be a fixed connection between the measurement result on the physical object and the digital twin. Models for linking the variables to a simplified result are also necessary. The large number of sensors allow redundancies to be set up via these models, so that on one hand, the result in the evaluation is more reliable, but on the other hand, sensors that fail can be partially replaced by the others to enable an overall picture in the digital twin. We have already come a long way in the last decades with the high voltage power transformers. The energy transition makes it necessary to know more about the medium and low voltage transformers and networks, and, if necessary, to monitor them with continuous measurement technology. I would like to point out once again that the future will be very demanding in the medium and low voltage levels. Therefore, digital twins of the transformers and the networks behind them can be considered in order to better observe the operational behavior.
Professor Hartje, what are the new tasks for the latest measurement technology in diagnosis and condition assessment?
Well, if we turn once again to the low voltage grid, we are particularly pressed by the fact that we expect a high generation share due to the energy transition. And here, a digital twin of the grid and the resources can easily supplement the information that was missing in the past by means of selective measurements and their linking in order to avert the threat of transformer overload, but also to monitor the power distribution, the voltage quality, and the voltage level stability, and thus to obtain better information about the utilization of the resources.
Okay, so how does the use of several sensors play a role in the digital twin?
For a digital twin, a large number of sensors are necessary to maintain a proper overview of the current operating status. In addition to electrical values, temperatures, and partial discharge activity, vibrations from additional devices can also provide important information. The multitude of sensors that record different physical values and the physical models in the digital twin makes it possible to make the result more reliable and to build up mutual redundancy. In short, redundancy helps to make data collection more reliable. Digital twins are parts of digital processes that will encounter in the digitalization of energy technology in the future. Optimization and the use of artificial intelligence require a good mathematical description of the physical models and processes.
Very good. Professor Hartje, what are some of the activities of international power industry organizations concerning the digital twin?
There are national and international activities on the digital twins. If you look in the literature databases, for example, INSPEC, there are currently 16 sources listed from 2022 on the digital twin of power transformers. But it seems important to me to also point out the activities at SIGRE. Currently, the SIGRE Joint Working Group A2/D265 summarizes various activities. This working group is chaired by Patrick Pichet. The final report is to be prepared by 2025. In Germany, there is a study group of the VDE heading the digital twin of power network coming to an end of their first step. They will publish a report end of May 2023.
Professor Hartje, could you summarize our discussion here about the digital twin? What are the most important points our listeners should remember?
Using the example of a power transformer, we looked at how the digitalization of energy technology can progress. To do this, the digital twin needs many sensors for different physical variables on the transformer. A good model description of the physical relationships and bidirectional communication. It can continuously compile and evaluate the information under supervision, but independently, and pass on information to the responsible persons. In this way, the digital twin helps with the complex management of daily tasks and relieves the burden on those responsible. We have kept in mind the international activities and also those of SIGRE. Even though we believe we have known the transformer in science and technology for more than 100 years, it is once again apparent that further research activities are needed to meet the increasing demands of the energy transition.
Very good. Thank you for that overview. Professor Hartje, thank you very much for this discussion in this episode of Energy Talks about the digital twin, with a focus on its use for the diagnosis and condition assessment of power transformers.
Thank you very much for your kind and good questions, Scott, which have given me the opportunity to shed light on some aspects of the digital twin of power transformers. Perhaps it has helped to make some concepts of the possibilities of digital twins visible and thus more applicable. We will probably encounter it more and more in the coming years in many areas of industry and the private sphere as well.
Very good. Thank you very much again.
Thank you.
And a big thank you to our audience for listening to this episode of Energy Talks. We always welcome your questions and feedback. Simply send us an email to podcast@omicronenergy.com. Also, if you like what you hear and have not done so already, please be sure to subscribe to Energy Talks on your favorite podcast platform to never miss an episode. Omicron has several years of experience in power system testing and offers you the matching solution for your application. This includes innovative solutions for electrical equipment diagnostics and monitoring, which can be used in support of digital twins. For more information, be sure to visit our website at OMICRONenergy.com. There, be sure to look under Applications to find matching Omicron solutions. Knowledge sharing is very important to Omicron. On our website, you can also find the latest papers on various power system testing topics, upcoming seminars and events, as well as training courses. Please join us to listen to the next episode of Energy Talks. Goodbye for now, everyone.